Spiderwebs look incredibly delicate. A single strand can shimmer in the sunlight, sway in the wind, and disappear from view if you look at it from the wrong angle. Yet despite their fragile appearance, these remarkable structures can stop fast-moving insects, survive storms, and support loads many times greater than the spider's own body weight. In this video, we'll explore why are spider webs strong, what they are made of, how spiders produce it, why different webs are built differently, and why these natural masterpieces continue to inspire some of the world's most advanced materials research. Right here, on History of Simple Things. When people think about a spiderweb's strength, they usually imagine that the silk must simply be an incredibly powerful material. While that's partly true, spider silk is much more complex than a single type of thread. Most spiders produce several different kinds of silk, each designed for a specific purpose. Some silk forms the sturdy frame that anchors the web to trees or buildings. Other silk creates the spokes that spread force throughout the structure. The sticky spiral, which traps insects, is made from another type altogether. Each silk is produced by specialized glands inside the spider's abdomen and exits through tiny structures called spinnerets. By combining these different silks into one carefully organized design, spiders create webs that are both durable and efficient. Instead of relying on one super strong thread, the web works because every strand has a specific job, allowing the entire structure to absorb stress without failing all at once. Spider silk owes much of its strength to its unique molecular structure. It is primarily made of proteins called spidroins, which contain long chains of amino acids arranged into different regions. Some sections fold into tightly packed crystalline structures that provide impressive strength, while other sections remain more flexible and elastic. This combination allows spider silk to resist breaking while still stretching under pressure. In many cases, dragline silk, the type used for a web's frame and for a spider's safety line, can stretch by around 20 to 30% before snapping. This balance of strength and flexibility is known as toughness, meaning the material can absorb a great deal of energy before it breaks. Weight for weight, certain types of spider silk are tougher than many synthetic fibers such as nylon and can rival or exceed high-strength materials in energy absorption, making it one of nature's most remarkable engineering achievements. The strength of a spider web doesn't come from its silk alone. It also comes from its design. A web is carefully arranged so that force is distributed across many strands instead of concentrating in one place. When an insect flies into the web, the impact spreads through the radial threads and surrounding spirals, reducing the chance that a single strand will bear the entire load. Even if one or two threads snap, the rest of the web often stays intact, preventing catastrophic failure. Engineers call this redundancy, and it's an important feature in bridges, buildings, and safety equipment. The web's geometric pattern also helps absorb movement, allowing it to flex instead of resisting every force rigidly. This flexibility means strong gusts of wind or struggling prey are less likely to tear the entire structure apart. In many ways, the web behaves like a sophisticated suspension system, turning individual threads into a resilient network. Spiderwebs are the result of hundreds of millions of years of evolution. Early spiders likely used silk for simple purposes such as protecting eggs or creating shelters before gradually evolving increasingly sophisticated webs for hunting. Over countless generations, natural selection favored spiders whose silk was stronger, whose webs captured prey more efficiently, and whose energy investment produced better results. Building silk is expensive because it requires valuable proteins, so spiders evolved to use only as much material as necessary while maximizing performance. Different species also adapted their silk and web designs to suit their environments. Orb-weaving spiders build symmetrical circular webs ideal for catching flying insects, while sheet-web spiders produce dense horizontal platforms, and funnel-web spiders create silk tunnels that allow them to ambush prey. These diverse strategies show that spider silk is not just strong, it's highly adaptable, shaped by millions of years of survival and refinement. Although spider webs are incredibly strong for their weight, their greatest advantage is not absolute strength, but intelligent design. A web is meant to survive long enough to catch prey while using the smallest possible amount of silk. Many spiders regularly inspect, repair, or even consume damaged sections of their webs, recycling the valuable proteins to build fresh silk. This efficient reuse reduces waste and conserves energy. Environmental conditions also play a role in web performance. Humidity can affect elasticity, while sunlight gradually weakens silk through ultraviolet exposure, prompting many spiders to rebuild their webs frequently. Despite these challenges, spider webs remain highly reliable because they combine adaptable materials with continuous maintenance. Rather than creating an indestructible trap, spiders have evolved a flexible system that balances strength, efficiency, and repairability. It's this combination of smart material properties and thoughtful engineering that makes spider webs such extraordinary natural structures. Spider webs prove that true strength can hide in plain sight. What seems like fragile thread is actually a remarkable blend of biology and engineering. Spider silk is both strong and flexible, and the web's structure spreads force across many strands. Evolution refined these designs for efficiency, while spiders repair and recycle silk to conserve energy. A glistening web is one of nature's smartest creations. Thank you for watching! If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.